a new series of videos. This series is a strange one, or rather anomalous, you might say. Yes, we are talking about anomaly detection. For the first video in this series, we're talking about an oldie but a goodie. We answer the question, what is Benford's Law? Benford's Law was first discovered by a Canadian-American astronomer named Simon Newcomb back in 1881. He discovered when looking at logarithm tables that pages starting with lower numbers were much more worn than other pages. He even published this result. Now, I know what you're thinking. Wait a second. Why is it called Benford's Law then? Well, along comes an American electrical engineer named Frank Benford in 1938. Fun fact, he wasn't even born when Newcomb first discovered the property. He noticed that leading digits on certain things do not occur uniformly, like they might think that they should. He published his test of 20 different data sets, ranging from surface areas of rivers, molecular weights, street addresses, and so on. And apparently people liked Benford more than Newcomb, so we call it Benford's Law. Here is a visual representation of Benford's Law. This is a distribution of first digits. Notice how the 1 has the highest probability, followed by 2, and it decreases from there all the way down to 9. Here is the actual mathematical view of the law. Basically, the probability of any first digit is log base 10 of 1 plus 1 over the digit itself. So the probability of the first digit being a 2 would be log base 10 of 1 plus 1 over 2. Now, maybe this concept of first digit is hard to grasp. Let me show you an example with some real data. Here I have gathered the GDP by country from the World Bank in nominal terms based on 2017. The United States is at the top, followed by China, Japan, and so on until we get to the bottom of the list of 190 countries. The leading digit is literally just the first digit. So for the United States GDP, it would be 1. China would also have a 1, Japan a 4, and it continues as we get all the first digits. If we were to graph these first digits on a histogram, what would we get? Would we get a uniform distribution? Nope. We would get something that looks like this. The number 1 occurs with the highest proportion by far, followed by 2, and so on. Here is Benford's Law plotted in a line on that histogram. It doesn't follow it exactly, but you can see the general idea of what Benford's Law is trying to state. In fact, there's a website called testingbenfordslaw.com that has tons of fun examples. If you're ever bored and want to lose yourself for an hour on a website, I highly recommend checking it out. But wait, wasn't this video about anomaly detection? Yes, it is. People have noticed that fraudulent transactions, which involve inventing new numbers or changing real transactions into fake ones, don't follow Benford's Law as some of them should. Criminals try to assume things happen uniformly, when in actuality, they don't. In fact, Benford's Law is actually legally admissible in federal, state, and local courts here in the United States as evidence. It has even been used to detect fraudulent investment return data for Ponzi schemes. Let's work through an example. Imagine you were in charge of reimbursing transactions submitted for work. You look at the distribution of first digits on scanned receipt totals. You also happen to know Benford's Law. That is when you notice something interesting. It looks like there is a lower number of 3s than expected, but a higher number of 8s. Looks like someone has been potentially fraudulently changing some receipt totals from things that start with 3s into 8s to get reimbursed more than they should. In fact, this has since been looked at from a statistical standpoint. We can compare actual data to see if it follows Benford's Law statistically. People tend to use the Pearson chi-square test for this, but this doesn't always work well with small samples, so you could also consider the Kolmogorov-Smirnov test of comparison as well. In fact, in our data example with reimbursements, the data is statistically different than Benford's Law, which leads us to really question what is going on.